Hello and welcome to the final episode, episode 25 of Chemistry in 15 Minutes or Less. My name is Audra, and this review lesson is on chapters 10 and 11, part 3, Gas Laws. Now before we get into the actual laws and equations to memorize, there are a couple of words we need to define to keep going. Pressure, barometer, and manometer. Now pressure is force per unit on a surface, which means that it's force per whatever area. Think of it like this. Like you've got a lid on a container and you're pushing down on it. Force per unit on a surface. That was one of the questions on the gas law test, is what units would you use for pressure? It would be surface area. Now a barometer measures atmospheric pressure. And a manometer measures the pressure of an enclosed sample. Now, as far as pressure goes, there are a couple of different units that you need to know, and the conversions between them. So 1 atmosphere, which is standard, which we'll talk about in a second, equals 101.3 kilopascals. Important to note that it's a kilopascal. Also, 760 millimeters of mercury, which is also equal to 760 torr. They're the same. You don't have to show the conversion between these because they're basically the same units. And one you don't have to memorize is 14.7 psi, or pounds per square inch. These 3 right here, or these technically 2 right here, you need to remember equal 1 atmosphere, which are all units of pressure. You will have to do conversions. Now, in the last 2 videos, you've heard me probably throw the word standard around a lot, because there's one more thing we need to talk about before we get into the laws, which is what's called STP Conditions, which are standard temperature and pressure. Now, for these to coincide, the standard temperature is 0 degrees Celsius, and pressure is 1 atmosphere. An important conversion to note is that 0 degrees Celsius is equal to 273.15 kelvins. Also, it's not degree Kelvin. I know we talked about that a long time ago, if you remember, I think, the second episode. But this isn't a very important conversion because later when we'll get into the R value, which is a constant, you cannot use Celsius or you will end up with the wrong value because you can't multiply something by 0 and still get a number other than 0 back. So now it's time for everybody's favorite to get into the actual laws we have to talk about. I'm going to define them, and then I'm going to show you the formulas, the use, and the conditions that go with them. First, we have Dalton's law of partial pressures. Basically, this states that the total pressure of the gas mixture is the sum of the partial pressures of the component gases, which is exactly what it sounds like. And now for the main ones we're going to talk about. Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law. First up is Boyle's law, which states that the volume of a fixed value of gas varies inversely with the pressure at a constant temperature. All that means is if you have a sample of a gas in a container like this, increasing the pressure decreases your volume. Decrease the volume here and it increases the pressure, so then on the other side, increase the volume and you decrease the pressure. Charles's law states that the volume of a fixed value of gas at a constant pressure varies directly with the Kelvin temperature. What that means is if you have a sample of gas, the volume as it increases will increase the temperature. The volume decreases will decrease the temperature. Because they have to vary directly. They're not inverse ratios where the less the volume, greater the temperature. Gay-Lussac's law states that the pressure of a fixed mass of gas at constant volume varies directly with the Kelvin temperature. Now that means the same thing. Increase the temperature, increase the pressure. Or back and forth. Charles, let me just quickly do. And the last one is the combined gas law, which puts all three of these together, which states or expresses the relationship between pressure, volume, and temperature of a fixed amount of gas. So that's a lot of words and a lot of confusing diagrams, so let's go over the equations that come out of these that you will need to memorize or remember for the final. We're going to do this slightly differently than how I have it on my sheet, but we're going to list the laws down this way. The formula you need to use with it, how you can use it, and the conditions that it requires. So like I said, the laws we will talk about are Boyle's, Charles's, Gay-Lussac, combined, and then there are two more, but let's go over the ones we've already talked about first. Now Boyle's law formula is pressure times volume is the constant value. Charles's law is volume equals K times the temperature. Gay-Lussac's is pressure equals K times T. And the combined gas law is pressure times volume divided by temperature, gives you back the K, or constant value in this case. So you use these in a couple of different ways. To use Boyle's law, P1 times V1 has to equal P2 times V2, which means that for this to happen, you have to have the constant temperature, as well as the constant value of the gas, or value of the gas in moles. Which means that if pressure 1 varies, then the volume that it times in this case, has to equal the finishing pressure and finishing volume, as long as it stays at the constant temperature. You use Charles's law in V1 over T1 equals V2 over T2, which means the starting volume divided by the starting temperature has to equal the ending volume divided by the ending temperature. Gay-Lussac's law is P1 over T1 equals P2 over T2, which means starting pressure divided by starting temperature has to equal ending pressure divided by ending temperature. And the combined gas law is P1 times V1 over T1 has to equal P2 times V2 over T2, which means that the starting pressure times the starting volume divided by the starting temperature has to equal the final pressure times the final volume over the final temperature. Now I realized I filled in the constants for Boyle's without going through the constants for the other one. But for Charles's law, you need a constant pressure, constant moles. For Gay-Lussac's, you need a constant volume, constant moles. But for the combined, you only need a constant moles, because the other ones take care of the other constants. Now there is one more addition to this we have to add, which is Avogadro's gas law. This guy keeps coming back, I know. But his formula says that the volume equals the constant times the n value, which is moles, and his equation is V1 over N1 equals V2 over N2, which means the starting volume over the starting number in moles has to equal the final volume over the final number of moles, which means you have to have constant pressure, constant temperature, because he's varying the volume and the moles. His does not deal with a fixed value of gas, which is why we did not talk about it with the other ones. Now there is one last law, but I'm not going to put it on the chart, which is the ideal gas law. Now the ideal gas law combines them together with a constant value called R. Because the ideal gas law is pressure times volume equals moles times the R value times temperature. Now, You can adjust this a couple of different ways to solve for pressure, volume, or even going through and solving for moles, or other ones and so forth, but the main equation is PV equals nRT. Now we've talked about pressure and volume and even the moles and the temperature. So what is an R value? Well, the R value is a constant, like Planck's constant or Avogadro's number, where it's 0.0821, and the units for this are atmosphere liters over mole kelvins. That is important to know. You can use this in any equation as long as you have all of your units in and that this value is the same. Now the last thing to talk about is one quick other memorization thing, which basically is 1 mole of any gas at STP conditions will always have a volume of 22.43 liters. Now, the equation to do this is you're solving for volume, which equals nRT over P, which if you're taking 1 mole of a gas times then your R value, 0.0821 atmosphere liters per mole Kelvin, times your temperature, which, like we said, you can't do the 0 degrees Celsius, so instead you take the conversion from earlier and do 273.15 Kelvin, all divided by the standard pressure, which is 1 atmosphere. So as you can see, your units cancel out this way, atmospheres cancel out, kelvins cancel out, moles cancel out, and in the final equation it will always come back as 22.43 liters. And with that little tidbit of information, that should conclude not only episode 25, but the entire series of chemistry in 15 minutes or less. I do hope this series was helpful, and I hope you can go back and rewatch other videos if they are helpful. Still, feel free to leave questions or suggestions in the comments below, and be sure to go back by following the in-video links, check out through the playlist again, or head over to my channel for the rest of the videos on chemistry review. This series took me a couple of days to make, and I do hope this helps you study, and I would like to say good luck to everybody on the final on Friday. Have a great night.